So good morning. So I'm Jean-François Guillemoles. I'm at IPVF. IPVF is a joint research center, Institute for Energy Transition in Palaiseau. And I'm the director of the UMR, the joint lab between CNRS, École Polytechnique, INSCP, and industrial partners that made up this institute. Since I'm the last speaker before the last, I'd like to thank the organizer for the great work, and so please join me in thanking all the Daniel, Laurent, Andrea, and especially Stéphane, who was completely exhausted this morning, so I finally can go home and rest a bit. So that was really great, and last time, for those who were there 2 years ago, there were some complaints about the weather, but I see that the organizers had to work very hard on that, and that they improved a lot, and I think many of us we could enjoy and maybe had a glimpse of on the Mont Blanc. So I have a talk on multi-junction. I will explain why it's interesting. It was not so much, it was a bit in the slides, and I felt it was necessary because a lot of institutes today, they have a big research program on tandem cells. So I think it's interesting to know what are the reasons for that, and why and how solar cells are designed. This is an old picture, but I think it's still not too bad. Yeah. So this is a chart, I think was made first by Martin Green, and here you have the cost of the module. So we didn't discuss too much about cost, but this is important, you may know, in the context of PV. And this is, we heard like Philippe Schulz, for instance, mentioning about how uncostly technologies are actually very costly. Okay, so so here you have, for different technology, the module cost and the power conversion efficiency. So the slope basically is related to the energy of production that you can have, like in dollar per watt here. This only includes the module cost, and you see that now we are around here $0.3 per watt peak. That's really, so that chart was made long ago, so actually all this is shifted. That's current technology are actually moved here. You have the limiting efficiency, silicon, shock liquizer, and others. And this doesn't include actually the balance of system cost. And if you shift that to account that you have some balance of system cost that also make some, say, as a additional real cost, you see that then the slopes, of course, becomes less steep, and so that the cost is more and has to be included. So in a way, if you want to make up to find the same cost here, you have to add quite a bit of efficiency to be on the same slope. Okay, so efficiency is a key driver for reduction in the cost. So an efficiency, you see, with shock liquizer is here. Then one is really, even if the module is free, one is already a bit limited in the cost that can be achieved. Now, since there was a competition for the oldest paper, I tried to make this one relevant. So actually, Becquerel, as you know, is a 200th birthday. He's dead, but he would be his 200th birthday this year. And at age 19, so this is a bit challenging even for the youngest among yourselves. At age 19, he discovered photovoltaic effect. Actually, in chemistry, I'm sorry, Uwe, that was the first solar cell was a chemical solar cell. This solar cell was actually an electrochemical reaction. You had some oxides on the cell, and when absorbing light, would deliver a current. So there would have been a celebration of that in 2 weeks. Unfortunately, as you know, this is now cancelled because of current pandemic. And actually, I'm very glad of this meeting because maybe this is the last large meeting that we can have, each of us, for some time. So let's enjoy. I mean, it's almost finished, but yeah, we can enjoy that. So he did this is his PhD, and why is it relevant? Because actually, if you look, it was one of the smart things that he was doing, he was trying to look at the effect of different colors on the photovoltaic effect. And so in some sense, and you would see that actually if you, so using colored glass or using refractive materials, you could see that if, for instance, violet light was active, but sometimes, most of the time, red light was not active. Okay? So you would see actually the effect of the wavelengths. And this is what sort of make it relevant for this, that, of course, photovoltaic effect is a quantum effect, depends on the wavelengths, and we see the importance of that. That's what I will discuss mostly. I will not discuss the Shockley quasar, but you heard a bit. You had a nice talk to start with. And I just want to mention that, as you know, I mean, if you take a solar cell, basically at optimum, 1/3 is converted, 1/3 is lost as heat, and 1/3 is lost during the collection of the carriers. You had tutorials, and we could discuss that yesterday. That's for a single junction, and so the limit is pretty much around 30%. Now, if you look how all these cells would compare to the limit, so the expected current and expected voltage, you see, so the limit will be here. So you have the maximum current and you have the maximum VOC fill factor. So that's the maximum power you can get. You can try to increase. You see all the technologies. Some are quite close to the limit already. And you can do with the material science carrier management, and you had excellent talks on that. Also on the light management to improve the current, also very excellent talks again. And you have a lot of material science that you can do to improve, and you had also a lot of excellent talks on the different material issues for the different materials to try to get to the limit. But this limit is only 30%. So actually, you know, maybe or not, but this chart from NRL plots the progress in the year. You see that you have indeed some solar cells that are above the limit. And actually, not only they are above the limit, but there are those cells that increase in terms of efficiency the fastest, except maybe perovskites. But you know, they are at the top, and they still there is a very strong increase, and there are something like 47%. I will not explain the 47%. I will stop at 38, and Daniel after me will explain how you can go even beyond that. And so that's the solar cell without concentration, and the concentration effect will be explained by Daniel after. The concentration effect is an additional boost, but without concentration already, some 38% is possible. So this is clearly already beyond the Shockley quasar limit. How can we do? So I will explain a few things today. So the first is I will try to introduce the optimal use of solar spectrum. So we don't, Shockley quasar is 30%. The Carnot limit, you know about the Carnot limit of conversion, efficiency conversion. So you take the sun, it's 6,000 K. If you have power conversion between the sun radiation at 6,000 K and room temperature 300 K, roughly, that would be 97%, 95%. That's a large number. Maybe there are some mistakes, but there is clearly a very big gap. I will try to show you where this, where the gap lies, and what can we hope for. Okay. Then I will discuss some multi-junction, the design and the performances, that possible designs that exist, to give you a broad overview and give you some more results. But I think the design rules will stay for quite a bit of time, so they are useful for you. The detailed performances of each technology may be not so important, and you can see that in the literature. So I will not give you too many numbers of that sort. They will be on some slides, but it's not so important. And then I'd like to spend a little bit time on how to model, because that's important, and how to characterize multi-junction, because that's a bit tricky. Okay, so what's optimal conversion of solar efficiency? You know, actually, that there are some losses. Okay, just mention them. Some light is not absorbed. So obviously, a good device should absorb everything. But then you know that if you absorb too much, you don't have the voltage, and that will not work. Everything goes to heat. Actually, it's very interesting that I digged out another old paper in the 80s, so that seems to be, actually, it's probably not an accident. It's like in the 70s, or it's, that's when really was, there was a lot of research on solar energy because of there was some oil problem already then, and people thought maybe we should transition to a different energy for different reasons. So there was a lot of effort and research done in that. So these are all charts, so maybe they don't look so good. But in essence, and I think Uwe had one like this in his slides, so maybe I spent some time to explain that. If I take the solar spectrum, okay, E, and I have the flux, okay, it would look something like this. Okay, I have some maximum, and the maximum is corresponds to this black body radiation. So it's something like this. If I am on Earth, I would have some, maybe some absorption lines. Okay, it doesn't matter. It's something like this. Now, if I integrate that, so that's a photon flux. If I integrate that over, and I integrate rather the energy actually, so that's not the power flux. Okay. The energy flux. If I integrate that over energy, I get something that would be like this. Okay, so I can erase this one. Okay, maybe not exactly, but you get the idea. Now, if I look, no, sorry, it's the photon flux. Okay. If I integrate the photon flux integrated over energy. So if now I consider I have a band gap which is very small, like here, potentially I can absorb everything. So that's all the current, okay? That's the current I could get, okay? If I have a band gap that's here, essentially I could hope for all the current. That's the current I can get, okay? It's the integral of all of that. So that would be the current. Of course, this is a limitation for the voltage. Okay, that's the current, and so this area is the maximum power, okay, I could get if all my photons could be absorbed and converted at the energy of the band gap. Now, of course, you know that there are some field factors, so some losses. So actually, if I include that, although I can absorb everything, possibly, but then I have some at maximum power point, I don't get EG, but I get less. There is a discount on that, and that makes this second curve here. Okay, this curve here is what you get. So now that means that at this band gap, that's the power. The surface here is the power that I can get. Okay, and this is the loss. That's Vm. So that's the voltage, the power times field factor, and that would be the difference. Okay, so if you look at like that, you have this. That's the maximum power that you could get. Now, if you think, okay, I make so, and these are the losses that are indicated. So the three losses: photon through, photon thermalized already, and photon loss, some energy loss during the collection. Okay, so we know that. So what would be the optimal power that one could get? Actually, if I get a band gap here, I can get all that power. And if if I get a band gap that's very high, I could get this, essentially this power. Okay. And because that's the integral. And now if I had some band gap which is a bit smaller, that can absorb what is under, so then I could get the difference. Okay, so there is still this number of photons to be absorbed, and that would be the power that one could get. Okay, and so on and so on. So in the end, you see that if you divide the spectrum in sufficient number of absorber layers, okay, that you have so many, so he did that for 37, you see that almost what you could get is the integral below this curve, okay? So essentially, this power, now if you compute this integral, it's because you know the solar spectrum, and this energy, and I show you how you can compute that curve. The integral below that curve under 1 sun is essentially 67% of the total of the incident power. So it's a large number. So actually, we discuss 20% solar cells, but we would have under 1 sun something like 67% available. What do we need to use that? Okay, so you have this original paper. It's a very interesting paper. So I want to make a very small model. I'm sorry, it's early and there are some formulas here, but bear with me. I will try to make it simple. You don't have really to look at this formula. You can just look at this one. It's pretty simple. This one states that if I have a two-level system, so I have a solar cell that can only absorb one single wavelength, okay, E. And when doing that, I pump one electron, or collection of electrons, from this level to that level. And these levels are connected to leads, and I can extract the current, and then it can do some work somewhere else and return here. So it's a solar cell that can only absorb one wavelength. If I'm at the relative limit in the Shockley-Queisser system and some very ideal assumptions, essentially, to get an electron out, I need a photon in. And when I have when I absorb a photon, I can get an electron out. And conversely, to get a photon out, I need a recombination, so I need an electron that comes here and recombine. Okay? So it's really a balance, and I can count the number of electrons I get is the number of photons I lose, and vice versa. So it's very simple. So I have this balance that electrical current is the difference between the flux, absorbed flux of photons, and emitted flux of photons. Now, the absorption flux of photons, it's something. So here I normalize it to the absorptivity of the material and to the density of state of the photons. That's I find it's a physicist thing. You like sometimes to. So it's all explained in this chapter. And here, similarly, if I look at the emission flux, it's a generalized Planck body law. You know about it. You heard about it. So it's that you've seen this formula. It's also very simple. It's the absorption coefficient. It's the density of state of the photon, and it's the occupation of the. This is just the Bose-Einstein occupation factor. So it's just the occupation factor of the photons in one state, in one photon state. And this occupation factor contains the temperature of the. You can ascribe a temperature to a photon flux and the chemical potential. And this chemical potential, because it's in steady state with the electron and holes, this chemical potential is related to the difference between the Fermi levels. I mean, this is just a chemical reaction. For a chemical reaction, the chemical potential of the products is the sum of the chemical potential of the reactants. Okay, so it's just equilibrium reactions. It's very simple. So in a way, I have something that relates by electrical current to my voltage. Okay, I can also relate that to the photon flux. So what I need to do to know what is the optimum for such a system is to look at the maximum. So the efficiency is the product of maximum power point at the maximum power point of the current and the voltage. That's P. Is divided by the incident efficiency. The power is current times voltage, or chemical potential of the photons times the difference of the flux absorbed and emitted. It's the same. Okay, you can look at it from electron point of view or photon point of view. And this, because if I work this out in terms of occupation factor of the photons in the flux, you see that this normalization factor goes out, and I can write that the optimum occupation factor for the photons is Fm. So that's the optimal occupation factor as a function of the average occupation factor of all the incident states. So it looks a bit complicated, but this Fm is now a Bose-Einstein function, so I can relate it to μm, and I can compute Im. And so I get this master equation that tells me for each number of incident photon, so that's my illumination of the cell, and for each energy, this Fm depends on the energy, okay? What is the optimum situation to convert a maximum of the state? So it's just, this is not maybe such a sympathetic equation, but it can be solved with any software that you have. You can also look at the, by the way, you can also look at the open circuit situation. And open circuit situation, you find that there, so it's simply G equals 0. It's very simple, that the optimum chemical potential, or if you like the VOC, is just the gap times 1 minus T over Ts at full concentration, if this F is 1. Okay? If F is 1 here, that's what you get. You get kind of Carnot efficiency. So that tells you, and from that you can plot. You can make a plot. This is my solar spectrum AIM 1.5, and I can plot what is the mu optimum, that is what is the optimum voltage, if you like, that a two-level system can give. And this is the curve. This is the curve for AM 1.5 in blue. For AM 0, just out in outer space in green, that's what you can get. And you see that this thing is pretty much linear. It doesn't have to be, but it turns out it is. It's pretty much linear as expected. I mean, the slope is 0.95 E. Why? Because it's 1 minus T over Ts, 95%, minus something. Okay, that's I will not discuss here. On average, if I integrate this curve over this solar spectrum, I get 0.7 for it's 0.7. That means for each photon, for each if I look at the energy I get for each photon that is incident on the cell, I get 70%. Okay, about 70%. That's okay. That tells you why you have like if I make a precise calculation, 67%. Okay, and that give me the limit on 1 cell. Okay, that would be if I would get 100%. That would be the curve. Okay, so the free energy, I can get for each two-level system depends on the photon energy, on the carrier temperature. Okay, that's the room temperature, and the intensity of the light. I can skip that. So it's this is nice theory. Do we have experiments about that? It's very difficult to make a solar cell with really a two-level system. But what you can do is you can take a gallium arsenide solar cell, a very good one, and you can illuminate this solar cell exactly at the band gap. Okay? So in that way, all the photons that are incident on the cell are absorbed. You don't get this loss. The photons do not thermalize because you absorb them near the band gap. You have no thermalization loss. Okay? So you would have eventually some collection loss. What are the efficiencies that are found experimentally? You see that this is for a gallium arsenide solar cell illuminated at the band gap. You have an optimum if you scan the wavelengths of the laser that you use, and you see that it's 55% have been demonstrated in the lab. For some concentration that was not well specified somehow, but okay, that gives you already, okay, that's already beyond Shockley quasar, and you see that you can relate here, and here you see same gallium indium phosphide, gallium antimonide, and you can have such demonstration, experimental demonstration. Now, this is a two-level system. Of course, I can do that for a two-level system. What is a Shockley quasar solar cell? It's a collection of two-level systems. Okay, now I have a lot of transition. This is a two-level system. That is also a two-level system, and so on and so on. I can look and I can sum it up, what I have, over all the two-level system. And if I have an absorptivity for this transition, and so maybe this would be maybe the same energy difference. The total absorptivity would be the sum of these two transitions. So it's really linear. I can sum it up. And I can look at the integral of that and do the same. So the concentration of electron would be density of states time occupation factor for the electrons. And again, I can integrate the emitted flux over all the energies. I can integrate the absorption over all the energies. And I get, with a Shockley quasar model, I get very similar formulas. And again, I can express that. Photons, electron, that was the game. And that's the reason why you have this correspondence. And luminescence is so efficient and useful because you have this correspondence really between the work done by the electrons and, in a way, the work that is lost by the photons. It's really, you can relate the two of them. Now, if I want to get closer to the two-level system, I can think of different systems that can use different wavelengths. So this can be done reversibly, I mean in a without or almost lossless fashion. For instance, one can use prismatic refractive material that's to disperse the wavelengths. More commonly, some people in a multi-junction would use different junction with different band gaps and would use some dichroic mirrors to separate the wavelengths. So that's mirrors that would be transparent in certain wavelength range and completely reflective in other wavelength range, in complementary wavelength range. Okay? So you can split the spectrum. You can split it in 3 parts, for instance, using such devices. Okay? So you have, like the 3 cells I shown you, a gallium arsenide, gallium indium phosphide, gallium antimonide. One would have the infrared part, one would have more the visible part, and one would have more the blue part and the UV part. And each of them could be closer, could work as close as possible to its optimum. I reduce the thermalization loss, I reduce the non-absorption losses, and so I gain. But this is very expensive. People have tried to do that. It's convenient to make experiment in the lab. I mean, you have optimized 2 cells, and then you put a mirror, and then you can test what you can expect. But it's very expensive to do. So it's better actually to stack this cell, and if you do, what you have, if I take the cell with the highest band gap, it can be made semi-transparent so that the blue light or UV light, the blue light is absorbed, but say the red and green light could go through infrared, and part of the visible could go through, is absorbed by a second cell that would absorb part of that and be again transparent, and so on and so on. And I can make many, and so I can stack several cells. Already that uses less space, and it avoids to have a complicated system with the dichroic mirrors and so on. My cells are used as a filter, but of course they should be transparent, highly transparent, for the part that they do not absorb. Something even better can be done is they can be stacked on top of one another and connected electrically in series. Okay, so now this system is in series optically. Okay, but I can have different. I have 2 terminals. I have 2 wires for each cell that I can look at the optimal power for each of them. In that case, I have 2 wires for the stack, and they are all connected in series. Okay, so if they are connected in series, the same current goes through. And I can again, but I will not detail, I can again determine what is the energy per particle, what is the voltage for each cell, what is the optimum for that, with very simple equation. And if it's in series, of course, same current across all the cells, and the power is expressed as the current times the sum of all the voltages. Okay, fine. Now, there is a question, if I have an infinite number of cells, and I don't care about putting them in series, I have no problem. Now, if I want to put them in series, really, I have a problem. I just mentioned they should see the same current because they are in series, right? So the same current should go through all of the cells. This is a very busy slide. So I will do it on the side. So you have this nice, that's for your record. I have this condition that I should have some, the same current. How am I going to determine if I'm not, what should be the band gap, optimal band gap, then one should use, okay? How am I going to determine what is the best combination? I found this very interesting paper and gives you a very simple answer. I will try to give you some rule of thumb for several things like this. One thing is that one observation, which is not obvious, is that actually if I look at the open circuit voltage, or if I look at, for the same reason, at the maximum power point, actually, and this I think, Uwe, you had the slide like this, you see that the voltage, because it's, it's the log of the short circuit current over the dark current. Actually, if I rewrite, this is a black body radiation, so it goes as exponent minus Eg over kT. G naught as this band gap, or multiple, but often ideally the band gap as also in the activation energy. So essentially, VOC you see, varies linearly to first order with the band gap plus something that also can depend a bit on the gap, but the main contribution is here. So VOC depends linearly on Eg, and what is less, and maximum power point voltage also, because it's roughly proportional to VOC. And short circuit current and maximum power port current, so that's the one I will use, is, as it turns, also roughly proportional to the band gap in the range we're interested in. That means between 0.5 EV to 2 EV, actually, the short circuit current is roughly proportional to the band gap. Okay, you have this red line here. It is as a coefficient. Somehow, okay? So if one is proportional to the other, actually I can make a plot like this, where I can say that then the maximum power point voltage is some kind of proportional to is a linear function of the current, okay, by eliminating the band gap. Okay, I have that, so I have such plot here, which is here normalized. Now, what is my optimum band gap? So Shockley quasar band gap. It's what you obtain if, of course, if my things is normalized. Okay, it's a straight line, so you know the maximum area. So the maximum power point is the maximum VMP times GMP. Is the maximum square I can include. So it's 1/2 of this normalized constant, whatever it is. Okay, that's fine. And indeed, you can find that the band gap, the efficiency, is not too good, but it's the right order of magnitude. So that's for one band gap. There is some, typically with this formula, there is a 5% error. But interestingly, also you can find the correct or close to an idea of what's the correct band gap. Now, what about multi-junction? Well, multi-junction, you can just use the same, just like the Henry plot I discussed. So this is the maximum power for each. So now I take one device. I must have some current that goes through. That should be equal to the current of all the other cells. I take the larger band gap, and the larger band gap, okay, would be something, that's the power, that's the current it gets, that's the power it can get. And I would look now, the next cell would absorb that much current, okay? It would have this difference of the current, and the third cell also this current, and would get this voltage. And now I have to see if I have such rectangles such that all these, their base are equal, what is the maximum surface that can be enclosed? And it turns out the answer is very simple. It's I have to divide my maximum current into n+1 if I have n cell. Okay? So in a way, it's the way to, in a way that's the share of the angles. Okay? You have to leave some photon away. That's the part that is non-absorbed. And it's roughly equal to the part that would be absorbed in this linear plot. Okay? In terms of IM. So that roughly gives you the distribution of band gap. Then you can, from this plot, calculate back for this very simple linear formula, what is the plot. The interesting thing is you see, and that's the one I wanted to see, because actually we will see that this is quite closely obeyed. And I think it's an interesting rule of thumb. If you want to have a multi-junction with n different semiconductors, you have to make n+1 slices of the spectrum. Okay, that are equal. Okay, you can make the calculation, and if you would do the Shockley quasar calculation, so these are the distribution of the band gap for 1, 2, 3, so on, that I've computed some time ago, and you can see how they distribute, and it's funny that actually this looks like at the end large number of band gap, a bit like the solar spectrum. Asymptotically, actually, you have something where the efficiency at n is the efficiency at infinity, so one sun would be 68%, sorry, and divided by something that is n+1, because A is roughly equal to 1. So it's, you have n slices that produce over n+1 slices of the solar spectrum, one of which do not produce. Okay, so that's you have, if A is 1, is exactly what I've told you. And A is really close to 1 for every concentration that you can look at. Okay, this simple thing, this simple scheme can also be used. I think it's funny, and it may be a topic for a tutorial next time. Okay, you can also use that to assess concentration effect, bifaciality effect, that if your bottom cell can also get light from the back, okay, or series resistance effect, because series resistance is another linear effect, and so on and so on. Actually, what is important there is actually if you take into account such concentration, bifaciality, series resistance, and other effects also, they all leads to change in optimal band gap. And that's the point I'd like to stop here, and I think it's a really important point, that actually I made all these calculations, shock equalizer, and they are really a guide, you know, that's to know about, but you see it's not so precise. And I will spend the rest of the talk explaining why this is not what you should use to make the cells. And although you see many papers have used the shock equalizer band gap to get started, very soon they discovered that they were not the optimal band gaps, because actually you have to take into account a lot of things. Well, of course, if you use the concentration, that's shift them down. If you have series resistance, it's also a change. If you have optical losses, and so on and so on. So you have really, but that gives you a rule of thumb and some kind of insights where to look for and what kind of material to look for and what to do there. Okay, so of course, real material, and this was, I think, has been explained during the week, are not shock equalizer materials. Okay, they are not real material. They are not according to shock equalizer. There are a lot of differences. For instance, there is significant parasitic absorption, and this is really important when you want to design the cell. Accelerated properties, and so that will shift also the optimum band gap. Non-relative recombination also would shift if you take into account. You can have also relative coupling. If your cell is quite relatively efficient, you see that one of the cell that are the cell on the top that absorbs would emit light towards the sun, but also towards the other cells. And if it's relatively efficient, it would change the current of the bottom cell, okay, of the cell that is below, that can also absorb this photoluminescence. So you do have, and we have devices that are efficient enough that this actually can be observed, okay? And of course, this would depend on where you use, what is the temperature of use, and so on. If you use, and I will come to that several times, because most of the device, and it's the most economical way to do, is to stack and series connect all the cells. That makes the stack quite spectrum dependent. Okay, they must have all the same current. But this partition of the spectrum, I can do for one precise spectrum. If I use a different spectrum, I will have a different partition, different optimum band gaps. Okay, I would require a different optical optimization so that really each cell gets the same current. Okay, and that's also, I have a cell. The band gap also changes with temperature. Okay, so if I use the cell at a different temperature, in a different environment, get a different spectrum. I mean, today I don't have the same spectrum as Wednesday when we had a beautiful day. Okay, and that means that my multi-junction that was optimum, say for when it's good weather, is now not optimum for another weather. Okay, and it's more dramatic when I increase the number of junctions. When I have only 2 junctions, it's okay. More or less, I can suffer, I can deal with some change, but the more junction, the more difficult it is. And that's maybe rule number 10. You had a lot of rules already this week. When you optimize something, the range over which you can use the system that is optimized becomes more narrow. Okay? So when you optimize something very much, chances are that this thing cannot, you restrict the way and the possibilities that you can use this system. Okay, state of the art. These cell multi-junctions, and some of you, you know, and you've been at the poster, so I won't be long on that. It can be used on concentrated photovoltaics. It has been used. This is now something that is less used, but there are already some hundreds of megawatts installed. It's also used in space, this type of technology. Surprisingly, there has been also some large area application. I'm sorry that there was not too much discussed about it, because that was a very powerful and manufacturing process at some point, but has now more or less disappeared. And as I mentioned, so actually that means that can be made cheap in a large area. And actually that's, as I mentioned, something that is thought of for the next generation of solar cells. For instance, at IPVF, we have a program to go 30% with modules by 2030 and at low cost. So good luck to all of us to reach that. But actually, it's on track, and not only our lab, but many labs working on that, and there is a lot of progress being made on that. So it might be possible. Okay, I've discussed already the different way of splitting the light. Okay, now if I look at real device, I should also discuss the way they are connected. So I mentioned that you can have 4 terminals. If I have 2 cells, I can have 4 terminals, 2 terminals, so 2 leads for each cell. I can have 1 lead and series connection, or I can have intermediate situation where I would have 3 terminals, so I could have the series connected and the extra current I can extract through 1 lead that would have a lower amount of current just to balance the current between the 2. And that way I could have, just with 3 leads, the same efficiency potentially as with 4. But as we see, it can give an advantage, other advantage than just sparing a lead that would not be that costly in the end. Okay, so this splitting, this is typically, for instance, a device. You would have 3 systems. So in the most common system is like using indium gallium phosphide top layer. Andrea showed you a lot of that. This is typically, this is a solar spectrum, and that's the power. That's the solar spectrum in power-wise, and that's the part that each cell would contribute to the total efficiency. You connect them in series, and now we have a problem. Actually, how can we connect 2 cells in series? Okay, in principle, it's done in solar modules. You have like a wafer of silicon. Okay, you have your wafer of silicon, we've seen. So you have a metal at the back, you have some grids at the front. Okay. And then I can take a wire, connect here. Okay, the top of this one with this one, and they are in series. What's the problem? Well, the problem is that I can't really use a metal because I'm stacking my cells and the metal is not transparent. Okay, so I have to find a way to have a transparent metal. Okay, and if possible, a large band gap. So there are actually one way of doing that. Okay, and maybe some of you know that. Maybe you know. I'm sure some can mention that, the name. So TCO, yeah, okay, it's good to have a TCO, but that's not necessarily what people would use. You can use TCO to make these tunnel junctions. What? I said it. So, okay, so maybe have you heard about tunnel junctions? Yeah, some, you know, okay. So it looks like that, okay, that you have all these cells stacked on top of one another, first cell, top cell, middle cell, bottom cell, and you have to connect them. And you can use a TCO, but if you would use a TCO, you would need a TCO that would be a good ohmic contact. You remember, you had the talk discussing that here I have a P-type semiconductor, here I have an N-type semiconductor, and I need a semiconductor, okay, that would be a good contact both on P-type and on N-type, making a good ohmic contact, okay? That might be counterintuitive. You remember the tutorials? We tried to discuss how to make contact on devices. Okay, that might be problematic. So actually what you can do to make a contact on P, it's good to take a P plus, okay, material, and then you take N plus material. Okay, so you have 2 highly doped material, and because they are highly doped, and you make a contact between the 2 of them, because they are highly doped, you have a high electric field, of course, okay? They are highly doped, so the space charge region is very small. Remember the SCAPS tutorial and all the tutorial that you had this week. And because the space charge region is very small, that means you have a huge drop, and that means that actually in the P-type side, the electrons on the P-type side, they are at the same energy and in close position in space to the holes here, to the electrons on the other N-type, N++, so highly doped N-type material, and so the electrons can actually tunnel. Okay, tunnel through, and at 0 volt it's something like this, so you have really a huge band bending. Okay, and when you bias, okay, then you have this electron, they can tunnel to the empty states in the valence band. And this IV curve looks like this. Okay, first you have these high rays due to the tunneling, And then you forward, and at some point this decreases because now these electrons see no state, okay, in front, so you have a decrease, but you start to have the normal diode current, forward diode current that you see here, okay? So you see that actually you can make a tunnel junction, but you have a small voltage drop, a cost, okay? You incur a cost here, that is this voltage drop across a tunnel junction. It's your contact resistance, if you like, so it's not perfect, so now it's, okay. So that's how it's done, and the best solar cells are really like this with 3-5 solar cells, and these are the efficiency. So you have 1 junction, 2 junctions, 3 junctions. Look here, okay, so here is so 29 and so on. So you increase the number of junctions and you increase, but you see you don't increase so much. You go now, I think as far as I know, the record is close to 39%. You can increase a bit by concentration somehow, but you see actually, so that the gain here, okay, is somehow not the gain this way is not so far from the gain that way. So still it's difficult, far from optimum. Okay, and you have here a report on all the junction. Where basically the message is whatever you take. I mean, if you take a 3 junction, this is the Shockley equalizer 1 junction, and you're always quite below what you would get, quite far remote yet from the system, the optimal system, the Shockley equalizer. Unlike for the single junction solar cells of gallium arsenide. 5 minutes, yes. 5 minutes. So I leave. We have. I take 5 minutes, and then we have the rest for questions. So it's a cost because you have to get lattice matching. You have single crystal substrates, so it's costly to do that. So that's a problem. But actually, there are some cheap way of doing that in line, and that was demonstrated by amorphous silicon technology. Some people have worked on that. And that's very powerful in terms of it's really an inline process, and you can do the first multi-junction, the second, the third one inline, and actually very cheap. The problem is that amorphous silicon is not such a highly efficient material, and even though you stack junctions, so I think the record was only 14% with 3 junctions, so you see it's very far, but in principle, it has been demonstrated that it can be done fast, efficiently, and so on. Okay. So in terms of processes, it's possible. One has to find the right materials now to do that. Okay, so cost. So the cost, of course, you have the cost for 1 junction, but if you have 2 junctions, you have more cost. I mentioned about the electrical losses from the tunnel junction. You have the optical losses. The intermediate layers, they do absorb light. So it's a problem, and when you add junctions, these costs add up. And also you have a decreasing marginal gain. So at some point, if you look at the cost versus the number of junctions where you would find some optimum, and that optimum at the moment is not very high. Probably 2-3 junctions is already the maximum. Then there is a lot of research now done because, as you know, silicon technology is reaching a plateau. So really we are very close also to, for silicon technology, what can be expected. But silicon technology, crystalline silicon technology now is very cheap. And as it turns, silicon is a very good choice as a bottom solar cell. So there is a lot of excitement now. Okay, let's take this technology that is very mature, very cheap, and let's put something on top. And you see that actually what you can expect is very close to the Shockley equalizer limit. Okay, using a silicon bottom cell. And you can look at it and start with 2. Okay, so these are tandem solar cells on silicon, IPAS, but you have already some realization at around 28%, for instance, perovskite on silicon solar cells, or even maybe a little bit more now. Okay, and 3.5 on silicon is 32% as far 3.5 gallium iron phosphide 32%, but gallium iron phosphide on crystalline silicon is also very close to that. Okay, so actually there is already some demonstration above 30% of tandem on silicon, which is a goal. Of course, that's a lab. Credit to Stefan Böschler from EMPA for this slide. Okay, rule of thumb number 2: actually, if you take a tandem solar cell, the top material gets about half of the power. And the bottom cell, you get half of the power of the bottom cell because it gets half of the current if you have a tandem cell, okay? They have equal current. So the bottom cell, for sure, gets half of its normal power. It's a pity if you have 25% silicon solar cells, you get only 12%. And then the top cell would get what it can get with the constraint that it has to be also with a transparent back contact. So roughly, as a rule of thumb, you say, okay, 2/3 of the power comes from the top cell. And that's a problem because we don't have as good top materials as we have as silicon, okay? Maybe gallium arsenide is very good, but gallium arsenide has a band gap which is far from optimum, as the optimum was explained. Shockley-Quasar optimum for a silicon solar cell would be 1.7, 1.8. Actually, if you do better calculation, probably the optimum band gap is larger than that, okay? And so, actually, we don't have as good top material as we would like, okay? So you have some calculation here. You have, so silicon perovskite tandem. You have 3-5 tandem. I can skip that. You have also ways to combine solar cells, not to do, I mentioned tandem, classical tandem where I stack the cells, okay? I mentioned, but I will not discuss, this is a bit complicated. So 2-terminal tandem in series, but actually if I use intermediate, interdigitated back contact solar cell, silicon, I have 2 contacts on the back. I can add a cell on the top, and with a tunnel junction here, and I can have a 3-terminal solar cell where I have 2 contacts here, and I have some exchange here, and that makes the interconnection of the 3 contacts much simpler. And also it has been shown theoretically, but also now there are some experimental demonstrations, that this can have an efficiency which is as high as the 4-terminal tandem. So that would be actually quite good. And it has some advantages that actually if you go to some version of that, you could get away or do away with a tunnel junction. Okay, there are some smart ways to stack because you have 2p and 1n material. So you have some smart ways to combine that at the end you can do away with the tunnel junction and some of the losses that go with that. Okay, maybe I skip that. I will this is just a tandem cell, a curious tandem cell where all the materials of the tandem are the same. I mean, you stack gallium arsenide materials, okay? And you make a tandem between just gallium arsenide and you just change the thickness, okay? And you can adjust the thickness so that all have the same current very easily. And this type of solar cells demonstrated 70%, so I just mentioned that for that, 70% efficiency, okay? It's interesting because sometimes you have a gallium arsenide solar cell and the band gap is a little bit too low for the silicon. So what can you do? You could stack 2 gallium arsenide solar cells to divide the current of the gallium arsenide so that it matches the silicon device. And then you have an efficiency gain that you can use a very efficient material with a solar cell. You have an additional advantage that I don't have. I will let you puzzle with that, but actually this also reduces some entropy production in the solar cell. In a normal solar cell, okay, you have a generation function that is like this. Okay, you have the absorption exponent minus alpha x. Okay, so you have a large number of carriers at the front and less carrier at the bottom. If I make one material to absorb that all, I would have an average concentration of the carriers, so I make an average voltage. Now, if I make a tandem cell and I use this thickness and this thickness, so that I have the same number of carriers, you see that here I have a high concentration of carriers, I get a higher voltage. Here I have a lower concentration than average, I get a lower voltage, but the sum of the 2 voltage is higher than the average one. So I get a higher power this way. Okay? That's because log function is a convex function for the mathematicians among you. Okay? An example also with amorphous silicon and OPV. So I should be finished. I leave, so there are a lot of losses. They are collected there. You have that have to be optimized. It's very important to model the cell because the parasitic absorption is very bad. And I leave the question of characterization. There's an excellent poster that was, by the way, got a prize, very nice prize yesterday. So about how to characterize multi-junction solar cells. some of you did the game, so you know that the current has to be equal in the cell, and that's a problem. That means that the spectrum has to be very carefully calibrated if you want to measure a multi-junction. That means also that there are a lot of artifacts. I mentioned them here, and I can discuss with them that if you want to measure EQE, quantum efficiency, it's not trivial, because the cell that you measure should not be limiting the current, okay? And there are some artifacts that are mentioned in the papers here. And the last thing I'd like to mention is that some groups, I guess maybe you did that also, with luminescence, you can study multi-junctions. Normally, in a multi-junctions, when you make an IV curve, you have the total voltage, the sum of the voltage, and the total current. So you get this total curve here, okay, the global curve, but you don't have access to the individual curve of the individual cell that makes the stack. But if you do luminescence experiments, as Laurent explained, from the luminescence, if it's calibrated, you get, and as I explained also, okay, the chemical potential of the light, the number of photons is related to the chemical potential difference of electron and holes in each of the cells. So you can get the voltage of the individual cell as you do the IV curve. So you can access the individual characteristic of each individual cell at one. Okay. And now. But I think anyway, because because we have plenty of time, because actually there is not much afterwards, after Daniel. I mean, no.